Greetings, mathematicians! Welcome to our second narrated PowerPoint. In the previous video, we recapped the grade 11 knowledge necessary to navigate new work. Note the alliteration. But now, without further ado, on to grade 12, three-dimensional trigonometry. But before you panic, or possibly after you've panicked just a little bit, never fear. 3D trig is really just using the trig concepts from grade 11 and grade 10 and applying them in three-dimensional scenarios. Perhaps the hardest part of 3D trig is being able to visualize the scenarios, which even though they are in 3 dimensions, have to be drawn in 2 dimensions so that they can fit on your page. Here's an example. There we go. An electricity pylon. I'm sure you've seen one lying around. What's the difference, you ask, between one electricity pylon and the next? Well, about 400,000 volts, I'd imagine. Moving steadily along. If we were to represent this picture for the purposes of a maths question, it would look something like this. We'd first need a line to represent the vertical pylon. There it is. Then this triangle at the bottom represents the horizontal ground on which the pylon is standing. Sometimes we draw lines from the top of the vertical pylon or pole or whatever it is down to a point on the ground such as that line, and sometimes such as that line. So what we end up with for the purposes of our maths question is something that looks like this, a bit of a pyramid looking diagram. Now the grey part over here, that's a horizontal surface. That's the ground, as it were. AD is a vertical line. Then line DC is a line from the top of the vertical pole or the vertical line or whatever it is down to the ground, which means that this red triangle here is actually a vertical triangle. Likewise, DB is a line from the top of the vertical pole down to the ground. So the white triangle on the left is also a vertical triangle. So what we have here is the corner. Imagine if you were looking at the corner of your room where the floor and the 2 walls meet. Something like that. Something you should note is that a vertical line is always at right angles to a horizontal surface. So this angle here, angle DAC, is a right angle. Likewise, angle DAB is also a right angle. But this angle here, the horizontal flat angle, BAC, can be any size. It doesn't have to be a right angle. Okie dokie. So here's an example of what a question might look like in three-dimensional trig. There it is. AB is a vertical pole. There it is. B, C, and D are all points on the same horizontal plane. That's another way of saying B, C, and D are all on the flat ground, as it were. AC and AD are ropes that run from the top of the pole diagonally down to the ground at C and D, respectively. And we're told what the lengths of those ropes are. This little dash, of course, means that AC is the same length as AD. So now we are asked to work out the distance between C and D. Give it a go yourselves if you're brave enough. You can try it. Pause the video and try it. Pause the video and try it. Now that you've paused the video and tried it, let's have a look at how we would answer this. First of all, I like to work backwards from the endpoint. If we are trying to work out the length of CD, that means if I look at triangle BCD, if I had the length of BC and the length of BD, I could use the cosine rule. That means I need to work out the length of BC and the length of BD. Thankfully, however, BC and BD are going to be the same length because in this particular scenario, triangle ABC is congruent to triangle ABD. So once we've worked out BC and we've worked out BD, then we can use the cosine rule to work out CD. So let's see what that looks like in practice. There we go. To work out the length of BD, this triangle, triangle ABD, is a right angle triangle, which means your standard grade 10 trig ratios will work. I've got the length of the hypotenuse, I've got this angle here, 15 degrees, and I'm trying to work out the length of the side opposite the angle, which means I must use my sine ratio. Sine is equal to opposite over hypotenuse. Fill in my values. I don't know what BD is, but I know that the angle is 15 degrees, and I know that the hypotenuse is 4.5 meters. Rearrange that using equation thinking and work out my answer. BD is 1.16 meters. There we go, blue box. Because, as we said earlier, ABD and triangle ABC are congruent, that means that BC will also be 1.16 meters. Another blue box. Now that we've got BC and BD, we can now use the cosine rule on the flat horizontal triangle at the bottom, triangle BCD. We can use the cosine rule on triangle BCD to work out CD. There we go. Fill in all of my values. Of course, BC and BD are the same length, which is why we see 1.16 repeated throughout. The angle B is 118 degrees. There it is. Work that all out, and my answer is 1.99 meters. Final answer. Look at it there. Fancy red box. Now we have a slightly more complicated example. It's the same general premise. We have a vertical pole, vertical line, a horizontal triangle, ABC. We have some information about these various lines and triangles and angles, and we're being asked to work out the size of that angle there. So again, I like to work backwards. If I'm wanting to work out the size of that angle there, then we can calculate the size of that angle if we know what the length of AB and AC are, because then we can use the cosine rule on this horizontal triangle. Now AC will be easy to work out, just like we did in the previous example using the sine ratio. But to work out AB on triangle DAB, we don't actually have much information other than that BD is 21 meters. So we're going to need to work out the length of AD using trig from triangle DAC, and then we can work out what AB is. Yes, you can read all of that at your leisure. Yes, let's see what that looks like in practice. First of all, to work out AC, like we did in our previous example, we just use the sine ratio because triangle DAC is a right-angled triangle. There we go. AC is 12.47 meters. Now we're going to work out the length of AD. Also using trig ratios. There we go. So AD is 14.34 meters. Right, once we have the length of this and we have the length of that, because triangle DAB is a right-angled triangle, it means we can use Pythagoras to work out the length of AB. There we go, using a little bit of the old Pythagoras to work out the length of AB, 15.34. Right, so now we have AC's length, there it is there. We have AB's length, here it is here. We can now use the cosine rule on triangle ABC to work out the size of angle alpha. There's the cosine rule. Fill in all of our values. Do some equationizing, some more equationizing. What I've done there, hello, come back cursor. What I've done there is I added these two together, then took the sum of those two to that side and subtracted, and ended up with negative 215.95. Then I divide both sides by negative 439.95, and I get this. Then I go second function cos of 0.49, and voila, alpha turns out to be 60.60 degrees. Well, how about that? Now, before we go any further, a little fancy red box, and then after that, a quick word from our sponsors. All Gold. It's salad in a bottle. Also, it delays the onset of prostate cancer. Moving steadily along. Here's another example. It says example 2, but actually, the more astute observers amongst you will note that that's example 3. Bob and Martha are standing 30 meters apart. They are looking at a tree. Perhaps it's in a vineyard. Perhaps it's Martha's vineyard. Who knows? The angle of elevation from the ground at Bob's feet to the top of the tree is 31 degrees. Martha is standing 20 meters away from the tree. The bearing from Martha to the tree is 48 degrees, and the bearing from Martha to Bob is 73 degrees. Determine the height of the tree. Before we go any further, here's some things we might have forgotten about that you'll need to know for this question. Yes, first of all, angle of elevation is the angle from the horizontal up to a line, and the angle of depression is the angle from the horizontal down to a line. Furthermore, bearing is using the degrees on a compass to locate one object relative to another. North is 0 degrees, east is 90 degrees, south is 180 degrees, west is 270 degrees. Right, now that we've remembered that, on to solving the question. Right, we need to first draw a diagram of the scenario. This is possibly the most difficult part of the scenario. So first of all, there's the tree. It's a lovely tree. There's Martha. I've said A Martha, but that's actually point A where Martha is standing. And there's Bob at point B. Now, the distance between Martha and Bob is 30 meters. And then from Martha to the tree is 20 meters. Then I'm going to draw a little line between Bob and the tree. And then we know the angle of elevation from the ground at Bob's feet up to the top of the tree is 31 degrees. And then for good measure, I'm also going to draw that line in there. But we probably aren't going to need to use that line. Okay. So, there is our tree. If we want to start solving this, we're going to need to work out what the angle is here. And we use the information about bearing that we were given in the question, that if the bearing from Martha to the tree is 48 degrees, so that's from north to this line, from north to line AC is 48 degrees, and the bearing from Martha to Bob, so that's going to be from north to this line AB is 73 degrees. That means the angle between them must be 25 degrees. Hey, there it is, the wonders of modern science. Okie dokie, let's try and solve this. First, we're going to use the cosine rule to determine the length of BC. How did I know to use the cosine rule? Well, look what we've got in triangle ABC. We've got an angle with the length of the two sides on either side of that angle. That means cosine rule. There it is. Fill in all the information, and wonder of wonders, BC is 14,58. Left out the units. Darn it, -1. Now that we know how long BC is, triangle DCB is a right angle triangle because remember vertical and horizontal are always at right angles to each other. So we can use standard trig ratios to work out DC. It's going to be tan because we're given this angle. We know how long the adjacent side is, and we're trying to work out the length of the opposite side. And tan is opposite over adjacent. So fill in our information, draw a little vertical line, do some equationizing, and there we get our answer, surrounded by a fancy little red box. How exciting was that? Right, now our last example, example 4. These kinds of examples are quite popular for examiners for some reason. It's no different from the other examples except that we don't have any numbers, we only have variables. There we go, there's our diagram. AB is a vertical line, there it is. B, C, and D are all points on the same horizontal plane, so they're all points on the ground. DC is K units long. Angle BCA, so that's there, that's this vertical angle here, is theta. Angle BCD, so that's the angle on the horizontal plane, is beta, and angle BDC, another angle on the horizontal plane, is alpha. And we have to work out the length of AB in terms of K, alpha, beta, and theta. Kabth, I suppose, is how you'd say that in Greek. But thank goodness we're not speaking Greek. Yes, it's all Greek to me. Now, we're going to use the same processes that we've been using in the past, but we're going to have a lot of variables around. So first, in order to work out AB, we need to know the length of BC. So we need to calculate the length of BC on triangle BDC. In order to do that, we're going to need to know how big angle B is over there. Thankfully, we use the fact that 3 angles in a triangle add up to 180. So that means angle CBD, that's that one there, is this. Now that I know that, we can use the sine rule to work out the length of BC. So K over the sine of angle B, that's that, will be equal to BC over the sine of angle alpha. That's that. Now, it looks all rather confusing because of the variables, but it's no different from what we've been doing previously. If I rearrange that to get BC by itself, we get that. So BC is equal to K sine alpha over the sine of 180 minus alpha plus beta. What we can do to simplify it slightly is to look at this denominator here, and if we use reduction formulas, the sine of 180 minus an angle is going to be equal to the sine of that angle. Oh, so now we have a length for BC. There it is. Now we can move on to working out the length of AB, because we have a right-angled triangle here. Remember, a vertical line and a horizontal surface always form a right angle. So we're just going to use a trig ratio. Again, it's going to be tan, because we have this angle. We know BC, which is the side adjacent to theta, and we're looking for the side opposite theta. So we're going to use tan. There it is. Substitute what we know. Well, we know that the angle is theta. We know that BC is that complicated looking thing. And then all we need to do is rearrange this equation to get AB by itself. There it is. That is the length of AB in terms of K, alpha, beta, and theta. Well, that's the end of that. I hope you found it informative. Okay, bye-bye. Oh, wait, I forgot my little fancy red box. Now, okay, bye-bye.